It is a pretty well-known fact that Albert Einstein was not a big aficionado of the quantum mechanics theories that were shaping up during his lifetime. Time proved him wrong in some ways because some of the quantum theories are actually being proven step by step. Beyond that, however, the questions posed by Einstein are still valid, and they provide quantum researchers with a point of orientation when it comes to the answers they are yet to give. If Albert Einstein was alive today, he would probably have converted to quantum physics, because even throughout his life his views on this theory changed. If his theory completely clashed with quantum mechanics at first, he used quantum concepts to explain some of his theories later on in life. More specifically, in 1935, his experiments revealed what he called spooky action at a distance, or in other terms, quantum entanglement. He then continued his experiments furthering the theory that quantum entanglement was only possible in certain circumstances. Unfortunately, however, he never got a clear answer to this follow-up, and it was left to future generations to reconcile the theories. It would be more than interesting to see what he would have to say today about the more recent discoveries in quantum mechanics experiments. Why do we accept quantum mechanics? Without a doubt, Einstein's work reshaped the world in so many ways that it would take an entire library of books to explain them in plain English simply. In the scientific community, and dare we say outside of it too, Einstein is seen as a sort of demigod, an irrefutable authority that nobody dares to touch. If Einstein's theory of relativity is so well regarded and accepted, why do we even bother with quantum mechanics then? What demon sets so many contemporary scientific researchers on the path of actually trying to reconcile the worlds of classical physics and quantum physics? The reason quantum mechanics is accepted and still a topic of discussion is that it manages to solve what classical physics couldn't. And, as it has been shown, it would manage to push the boundaries of knowledge and technology beyond the edges of the imaginary, into a spectrum we only dared to touch our thoughts until not very long ago. September 7th, 2014 might have seemed like any other day of fall in the Northern Hemisphere. The leaves were probably slightly yellow by then, and the heat of the summer was slowly starting to wear out. Maybe it even rained a little in the morning, and by the time cities were waking up to life, the fog of a slightly chillier night vanished, leaving room for a perfect day of autumn. Everyone must know that September 7th, 2014 was the day the theory of everything officially saw the light of day. You might have heard about it because there was a movie on the life of Stephen Hawking. Or you might have stumbled upon it long before the movie came out. However, what is important is that the theory of everything is one of the most important attempts at unifying both the theory of relativity and the quantum theory. What was initiated in the 1920s by Albert Einstein started to make sense 8 decades later under the hands of Stephen Hawking. The theory of everything is perhaps one of the most ambitious projects ever. It is one of the theories that is bound to change every single little thing, not just in physics, but in science as a whole, and soon enough, in humanity's perception of pretty much every area of their lives. The theory of everything tries to finally build a bridge between quantum mechanics and the theory of relativity. Some would even dare to say that it will tell the mind of God, Marshall 2010. And that it will hold the key to humanity answering the questions it has been trying to answer for a very, very long time now. There are several candidates for the theory of everything. Some of them are implausible to be proven in the equation or in practice, but some of them stand out as sane options that might be the final answer to everything. One of these we would like to take the time to name the 2 most important contenders. As we draw close to the conclusion, we believe it is important for you to know what the most important work in physics is doing now, and as such, we will take the time to expand just a little bit on these 2 theories. One of them is called string theory, and what it says is that there is a 10-dimensional space we are living in. That sounds more than mind-boggling, we know, but wait until you hear more of it. If you're impatient, you can jump to chapter 17, but I suggest you keep reading on. In essence, the theory of everything relies on quantum gravity, and it aims to address a wide range of questions in fundamental physics, such as what is going on with black holes, how the universe was formed, how to improve nuclear physics, and how to handle condensed matter physics better. Ideally, string theory will unify gravity and particle physics, one of the main points that have to be bridged between classical physics and quantum mechanics. At the moment, however, it is not clear how much of this theory can be adapted to the real world and how much of it will allow for changes in its details. The other theory competing with string theory for the title of the theory of everything is the loop quantum gravity theory. This paradigm is heavily based on Einstein's work, and it was elaborated towards the middle of the 1980s. To understand it, you need to remember the fact that, according to Einstein, gravity is not a force per se, but a property of space-time. Up until the loop quantum gravity theory, there have been several attempts to prove that gravity can be treated as a quantum force, like electromagnetism or the nuclear force, for example. However, these attempts have failed. If physicists manage to prove the loop quantum gravity theory, space-time will be pictured with space and time being granular, which would consequently mean that a minimum space exists. In other words, according to the loop quantum gravity theory, space is made out of a fine fabric of woven finite loops called spin networks. Although string theory seems to be a lot more popular in mainstream media, mainly because of some of its properties are quite popular themselves, even outside scientific circles, like Michio Kaku, for example. The loop quantum gravity theory should not be dismissed in any way. Most of its implications are related to the birth of the universe, the reason for which it is also called the Big Bang Theory, and perhaps the reason for which the eponymous TV show was called that way as well. The evolution of quantum physics. During the 19th century, crystallographers and chemists tried to prove the existence of atoms. Still, it was not until the beginning of the 20th century that they were finally brought to light, thanks to X-ray diffraction. To model them, the quantification of the matter is a compulsory passage which gives rise to quantum physics. Quantum physics has brought a conceptual revolution with repercussions up to philosophy, questioning determinism, and literature, science fiction. It has enabled several technological applications: nuclear energy, medical imaging by nuclear magnetic resonance, diode, transistor, integrated circuit, electron microscope, and laser. A century after its conception, it is widely used in research in theoretical chemistry, quantum chemistry, in physics, quantum mechanics, quantum field theory, condensed matter physics, nuclear physics, particle physics, quantum statistical physics, astrophysics, quantum gravity, in mathematics, formalization of field theory, and recently in computer science, quantum computer, quantum cryptography. Quantum physics is known to be counterintuitive, to shock common sense, and to require arduous mathematical formalism. Feynman, one of the greatest theoreticians specializing in quantum physics in the second half of the 20th century, wrote, "I think I can say that no one understands quantum physics." The main reason for these difficulties is that the quantum world, limited to the infinitely small but which can have repercussions on a larger scale, behaves very differently from the macroscopic environment to which we are accustomed. Some fundamental differences that separate these two worlds are, for example, quantification. A certain number of observables, for example the energy emitted by an atom during a transition between excited states, are quantified. That is to say that they can only take their value in set discrete results. Conversely, classical mechanics most often predict that these observables can take on any amount continuously. Wave-particle duality. The notions of wave and particle, which are separate in classical mechanics, become two facets of the same phenomenon, described mathematically by its wave function. In particular, experience proves that light can behave like particles, photons highlighted by the photoelectric effect, or like a wave, radiation producing interference, depending on the experimental context. Electrons and other particles can also behave in an undulatory manner.